Hello everybody, Justin Miller, Oxford College Physics. We're going to be looking at some momentum and trying to understand a little bit more in depth why it's such an important quantity. So let us go back to something from way back, Newton's third law, and we're going to revisit that and kind of take a nice look at it. So we have ourselves Newton's third law, which ultimately said when two or more particles interact, the forces they exert on one another are equal in magnitude and opposite in direction. Let's just write that down. Two or more particles interact, the forces that they exert on one another are equal in magnitude and opposite in direction. I push on this that way, it's pushing back on me that way. There's a contact force going on, and when two objects are contacting one another, they're exerting forces on one another, equal magnitudes, opposite directions. That's ultimately what this is saying. It doesn't necessarily have to be a contact force. Nonetheless, we got ourselves Newton's third law there. So let us look at this. We're going to take ourselves two objects that are isolated, so there's no external forces acting on them, and we're going to set them on a collision course, so they are going to interact with one another. Two different masses, M1 and M2, on a collision course. So let us take this. We're going to say, consider two masses that will interact by colliding. And let's just say this is going to be one-dimensional here, keep things simple. We're going to take ourselves an M1 with some V1 initial hat. So it's initial velocity for M1. And then we're going to take ourselves an M2, and it's going to have a V2 initial hat, and it's going that way so that they will ultimately collide. So we got before collision. Then we have during a collision. Now, when they're colliding, they're contact one another, and they're exerting forces on one another. So at some point, we have that they are in contact. We've got ourselves an M1 and an M2. And what do we have? We got forces. Like we just said, we have a force on M1 due to M2. We'll call that the force that M2 exerts on M1, we'll just call it F21 hat. And then we've also got this force on M2 due to M1, we'll call that F12 hat. So we've got those two forces there, the forces of interaction. And we note that those forces are equal in magnitude, opposite in direction via Newton's third law. So this is during contact, or during collision. That collision is going to take place over some time interval t, right? They're contacting one another for the same amount of time. What that time is irrelevant. And the fact that the force is going to be varying over that time, or could possibly be varying over that time, is irrelevant as well, as we've already shown with impulse, changes in momentum. So what's going to happen with these two objects after they collide? Well, a bunch of different things can happen. We're going to keep this 1D. But let's just say that after they collide, they're going to have different velocities, right? They could be both traveling that way now with different speeds, or traveling in opposite directions, or possibly they could even go through one another. It's possible. Maybe one's jello and one's a rock. Doesn't matter. Let us just say, for argument's sake, that we've got this going on. We've got an M1 that will have a V1 final hat going that way, and we've got an M2 with a V2 final hat going that way. Just to put something in, that they have different velocities after. So after collision. So let's take a look at this. We've got a change in the object's momentums from here to here that is due to this interaction that takes place. This is what we want to look at. So let us look at the impulses on these individual objects. So come back over here and we'll say impulses. Well, we're going to take I1 and we'll just take average. The average impulses, right? Impulses due to the average net force, whatever you want. Well, I1 is going to be equal to the force exerted on mass number 1 over some time interval. So we will take this as being F21 hat times delta T. So this again, impulse on mass 1. And then we've also got that there's an impulse on mass number 2. Well, that is going to be the force that exerted on mass number 2 due to mass number 1, which again we're calling F12 hat, over some time interval, delta T. We could call that delta T1, delta T2, just to be on track with this. Impulse on M2. Well, what we should note with this is that the time intervals are equal. Delta T1 must be equal to delta T2. They're in contact with one another for the same intervals of time. And we've also got these forces here, F21 hat and F12 hat, they have to be equal in magnitude, opposite in direction. So what we have here is F21 hat is equal to negative F12 hat. Right? We just write, hey, there's a negative sign in between them, that's directional, there we go. So what we're going to do is take this and we're going to rewrite a couple things. Let us say that this is sort of irrelevant. Delta T1 is equal to delta T2. Let's just call it delta T. And let's go ahead and make some switcheroos here with some things and see what we can do. So let's make some more room. And we can write that impulse number 1, I1 hat. We should have hats there, sorry. Hat. I1 hat is equal to, well, we've got F21, we'll keep it with F21. F21 hat times delta T. And what do we know about the impulse? Well, if the forces are net forces, because these are isolated systems and the only force of interaction is between the two objects, then we note that the impulse produces the change in momentum, right? So we're going to say that these are net forces. This is an isolated system. No external forces. No external forces are present. So, with that, this being a net force, this is producing the change in momentum of object number 1. Net force on object number 1 times the time interval over which it acts produces the change in momentum. All right, that's good. Well, what else do we have? We've got the impulse on I2. Well, that is equal to F12 hat delta T, but we can write F12 hat delta T as negative F21 hat delta T, and that is going to produce the change in momentum of object number 2 because that's the impulse on object number 2. So what do we have here? Well, look at this. This and this. What's the difference between those two? They're opposite in sign, right? Oh my gosh, we have that, that's it. The delta P1 is equal to negative delta P2. Because there's just a negative sign in between these. So delta P1 made negative is the same thing as delta P2. So let's take a nice little look at this right here. because this is going to be where we extract out some nice, meaningful relationship here. So let's expand this out here. I'm just going to go ahead and rewrite it. We have the delta P2 hat is equal to negative delta P1 hat. All right, and we know that delta P2 is going to be equal to M2 V2 final hat minus M2 V2 initial hat. So we can expand this out. We'll do it in momentum first. Let's do this. Not confuse things here. So this can be rewritten as P2 final hat minus P2 initial hat, and that is equal to negative P1 final hat minus P1 initial hat, negative of the quantity there. And what do we have? Well, this is just M2 V2 final hat minus M2 V2 initial hat, which is then equal to, we'll distribute this negative sign through, this becomes minus M1 V1 final hat, and then this one becomes plus M1 V1 initial hat. So written out in terms of the individual momenta before and after the collision for the two objects, this is what we have. Let's further rearrange some things here. Let me put all of the initial values on one side and the final values on the other side. That is, hey, there's an initial value. Let's take this, throw it on that side with this initial value for mass number 1 and mass number 2. Let's take this final value and put it on this side so we have the final values for mass number 1 and mass number 2 regarding their momenta. So we can rewrite this as M2 V2 final hat plus M1 V1 final hat is equal to M2 V2 initial hat plus M1 V1 initial hat. Let's take a look at what this is. This is P2 final hat plus P1 final hat is equal to P2 initial hat plus P1 initial hat. Well, look at this. We've got something that's conserved here. We have the total final momentum of the system is equal to the total initial momentum of the system. This is P total final. Let P T sub F hat be equal to total final momentum of the system. And P total initial be the total initial momentum of the system. What can we do with that then? Well, from this, whoosh, we have then that P total final hat is equal to P total initial hat. Total linear momentum is conserved. Whatever the final momentum is equivalent to whatever the initial momentum was as a whole for the entire system. This is what makes momentum an important quantity and desirable to define and look at, because in systems in which the force of interaction between the two objects is the only force, momentum is a conserved quantity. And that can be utilized to solve out problems and harness relationships between things. It's a really, really important aspect there. So this can be rewritten further, because what we can do is we can take P total initial, subtract it from both sides. So we can also write this as P total final hat minus P total initial hat is equal to delta P total hat is equal to 0. Total change in momentum of a system that is isolated with particles interacting is 0. Conservation of total linear momentum. And that's what we wanted to get out of this, was just that. So, overall, what we're going to do is some problems that involve collisions, and collisions that are ultimately of objects that are isolated, so that the forces of interaction substantiate the net forces. And then we've got conservation of total momentum, which allows us to figure things out like, hey, what are the final speeds, or what are the masses, or what are the initial velocities, stuff like that. So we'll come back and start looking at some collisions, but there we go. We've got some conservation of linear momentum. Fantastic. All right, so what we want to look at is some collisions and ultimately define the types of collisions that we're going to investigate and utilize in problems. So let's just do that. Types of collisions. Ultimately, there's 3 kind of generalized types of collisions, and we'll just go through them and look at the conditions that satisfy them. The first type of collision that we'll look at or define is known as an elastic collision. An elastic collision has 2 things that it satisfies. Total momentum of the system is conserved. And total kinetic energy of the system is conserved as well. So, we'll just consider 2 objects, but really this is for any number of objects interacting. For 2 isolated objects, have to be isolated for total momentum to be conserved. 2 isolated objects. Colliding, we have then this. Delta P total is equal to 0. That's total conservation, or conservation of total linear momentum. So this ultimately breaks out to P total initial hat is equal to negative P total final hat, which goes to M1 V1 initial hat plus M2 V2 initial hat is equal to negative M1 V1 final hat plus M2 V2 final hat. The negative sign there comes from the change in momentum being, excuse me, no negative sign. Oops. What's going on here? What's going on? This is already P total initial minus P total final. Vice versa. All right, anyway, no need for that. There we go. Total initial momentum is equal to the total final momentum. All right, and we have delta KE total is equal to 0, which says then that KE total initial is equal to KE total final. Well, the total initial kinetic energy is the sum of the individual initial kinetic energies, which will be equal to then KE1 initial plus KE2 initial, which is then equal to KE1 final plus KE2 final, which we could expand out into looking rather large, but that's okay. We've got a 1/2 M1 V1 final squared plus 1/2 m2. Let's do initial. v2 initial squared is equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Final, initial, kinetic energies are great. So ultimately, when we have an elastic collision, we've got this is the case, and this is the case. Now for elastic collisions, ultimately have things just collide, don't lose any overall energy. That's basically that, which isn't a super realistic type of case. There's generally some amount of energy loss, but it is decent models for certain systems. Ultimately, what do we have? We got a system of equations that involve masses and velocities, initials and finals, right? Well, we're not going to go through all the algebra because it ends up being a lot, but it can be shown that utilizing those two expressions and doing some simultaneous solving here, that we can write expressions for what V1 final and V2 final are in terms of the masses and the initial velocities. You believe that? All right. It can be shown that V1 final hat is equal to M1 minus M2 divided by M1 plus M2 times V1 initial hat plus 2M2 divided by M1 plus M2 times V2 initial hat. If we know what the initial velocities are of the two masses, we know what the masses are, we can figure out what the final velocity is based upon those two expressions. And furthermore, V2 final hat is equal to 2m1 divided by m1 plus m2 v1 initial hat. And we've got a plus m2 minus m1 divided by m1 plus m2 v2 initial hat. So, kind of boring in the end when we got an elastic collision, because if we just want to know the final velocities, it's plug numbers in and compute what the answer is. One thing you have to be careful of, even with something like this, is these are velocity vectors. Generally speaking, we'll just be looking at things in one dimension, but you can ultimately expand this out to 3 dimensions where there's x, y, and z components, or I hat, j hat, k hat components, and linear momentum has to be conserved in every dimension. At any rate, even in one dimension, you have 2 different directions something can go. Positive I hat versus negative I hat. So you have to be, again, careful with these quantities here. These aren't just numbers, these are vectors. So be aware of that. Not that though, that's our, excuse me, that's our first type of collision that we can have, the elastic collision. And then we'll go on to the second, and then the third. The second type of collision, a little bit more realistic, is called the inelastic collision. Inelastic collision, again, has some conditions here. We have conservation of total linear momentum. Linear momentum, total linear momentum is conserved. But total kinetic energy is not. Generally speaking, when 2 objects collide, you'll find that kinetic energy is lost. lost to things like sound, heat, permanent deformations. Think of cars running into each other. Momentum's not conserved, right? Because, well, things get all warped, work goes in, or energy goes into disfiguring things. There's lots of sound made, there's lots of heat produced in the deformations, and in those particular cases we have kinetic energy is not conserved. However, there can be cases in which kinetic energy is not conserved but is not reduced. That is, that kinetic energy is increased. That involves having some sort of stored energy in the system to begin with that's released during the collision. We can still have the linear momentum conserved in that case, and kinetic energy actually increases. You just have to be aware of what's going on in the particular system. But in general, we just have inelastic collisions. Linear momentum is conserved, but total kinetic energy is not. And again, this is all under the pretense of an isolated system. The only force of interaction is between the particles themselves. So, for again, two isolated masses, we will have conservation of total linear momentum, p hat total, delta p hat total is equal to 0, which ultimately gives us m1 v1 initial hat plus m2 v2 initial hat is equal to m1 v1 final hat plus m2 v2 final hat. Again, being careful that those velocities again are vector quantities, and delta k e total is not equal to 0. So we can have ultimately that ke total final minus ke total initial is equal to some number. And depending on whether that number is positive or negative is really correlated with, was the overall energy increased? Did something give more energy to the system, or was energy taken away? With the latter being the more typical of the two, things collide, energy is lost, or kinetic energy is lost, transformed to other forms. So the number is negative. Kinetic energy is lost. If the number is positive, kinetic energy is gained. And then we got it. Then we had it, excuse me. So with this, we still expand these out, and this can be written as 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. There's ke total final. Then we have minus ke total initial, so we have minus 1/2 m1 v1 initial squared minus 1/2 m2 v2 initial squared is equal to some number. So that's all expanded out. And there we've got our inelastic collision. All right. Lastly, we have what is known as a perfectly inelastic collision, because it's just perfect, of course. What does that mean? Well, let's look. Number 3. We have conservation of total linear momentum. Total linear momentum is conserved, and the objects stick together after the collision. that is the big sticky part with this particular type of collision. They form one common mass after they collide. And we will always have that there is some amount of energy lost due to them sticking together. There is always kinetic energy lost. Due to them sticking together. So when we have these perfectly inelastic collisions, we're not going to say that there's other energies that are subtracted or imparted into the system, other than kind of like this binding energy, I like to think of it as. When objects collide, they don't want to stick together. There has to be some mechanism that makes them stick together, and that ultimately extracts energy from the system itself. So we will only be considering that energy when we're talking about changes in kinetic energy regarding perfectly inelastic collisions. So with this perfectly inelastic collision, again, got that delta P total hat is equal to 0. This looks a little bit different now, because we have the total initial momentum being equal to the total final momentum, but the objects stick together and form one common mass. It's one common mass, it moves together as one mass, right? So we have that M1 V1 initial hat plus M2 V2 initial hat is equal to the quantity of M1 plus M2. There's the combined mass times some singular velocity after the collision. So form one common mass with one common velocity afterward. So that's kind of nice. That actually makes problem solving with this pretty easy. And delta KE, say due to sticking, is equal to, well, we've got ourselves the final kinetic energy minus the initial kinetic energy, 1/2 M1 plus M2 V final squared. There's the total final kinetic energy of the system minus, well, the total initial kinetic energy of the system, which is the sum of the individual kinetic energies initially. 1/2 M1 V1 initial squared minus 1/2 M2 V2 initial squared. Oops, V2 initial squared. And this will be equal to the number that is negative, which represents the amount of energy required to make the objects stick together in the first place. So there we go. There's our 3 types of collisions in general, and what we'll do here in a bit is look at some problems involving them. All right, so that's it. Thank you very much.